Hello. In this simulation, I'm going to try to illustrate the difference between a small signal and large signal, AC effects and limitations of operation amplifiers. The AC limitation that we have, which is a small signal limitation and it's a linear limitation, is the finite bandwidth, meaning the large gain of the operation amplifier starts falling off rapidly and to the point where you have no gain at all, the unity gain frequency. Okay. Now, that limitation is linear. You have a sinusoid at the input, you're going to get a sinusoid at the output of the same frequency. The output, the magnitude and the phase is going to change, and you are going to have a decrease in the expected gain. Differently from that, you have the slew rate limitation, which is a large signal, AC, nonlinear distortion, as we are going to see. So let's start with the slew rate, because we already saw at the AC limitation, the limited bandwidth. The slew rate, if you recall, has to do with the rate of change of the output. So what I have here is just a voltage follower. I put a pulse at the input. I should expect, since I have negative feedback, meaning a path from the output back to the negative input, if this was an ideal op-amp, the output will be identical to the input. So let's do a transient analysis. And what we are seeing there is the input and the output. And you zoom in. There you go. You see an input that is a step function. You see an output is not able to keep up. Okay. Now a 741 has a slew rate. It's going to depend on the particular 741 and the model. And then there are variations. But normally it's around 0.5 volts per microsecond. It's not going to, in this case, it looks like to reach 0.5, it takes them almost a microsecond and a half. It's almost, in this case, we are at 0.3 volts per microsecond. That's the maximum rate of change of this operation amplifier. That's the slew rate. Now, when you have that limitation, you could imagine that if you put a sinusoid, as you keep increasing the frequency, it gets to a point that the rate of change, the derivative of the output, as a function of time, the maximum, is not going to be able to keep up. And so you're going to distort that sinusoid. And that's the full power bandwidth, or the slew rate limiting frequency, that is given as the slew rate divided by 2 pi V output. So it's going to be a function of the output voltage, and the larger it is, the more you're going to see it. So let's go ahead and change the pulse to a sine wave. I'm going to do a frequency, amplitude of 1, and a frequency, let's say 10 Hz, for instance, okay? 10 kilohertz. So what do we expect? The input is a sinusoid, this is a follower, the output should be a sinusoid, the gain is 1, right? There's no gain, the input has a gain of 1, the output should have a gain of 1. So here we have our input, and here we have our output, as expected. Perfect. Now, the slew rate limiting frequency, if we increase the output, or if we increase the input, in this case a follower, we increase the output, what we're going to see gets to a point that that's too fast, the change that you need to in order to achieve that frequency, and so you are going to, that the slew rate manifests in a nonlinear distortion. Look at it. Input, sinusoid, output, non-sinusoidal. You get a triangle, just simply because you have the ramps. Okay? That's a nonlinear distortion. It's exactly the same thing as we did before. Before we have a step. In this case, we have a sinusoid. The rate of change is higher. This is the maximum rate of change. In this case, it's 0.3 volts approximately per microseconds, what you're able to see. And so you're going to get a triangle. Looks like you're losing gain, but that's not due to the bandwidth, the finite bandwidth. It is due to the slew rate. And if you make this even larger, like 12 volts, you're going to see it even more. Okay? So a slew rate and related full power bandwidth, or a slew rate limiting frequency, the frequency at which you start to see that nonlinear distortion. Now, if I do an FFT at the output, you start seeing harmonics. Let me just put it in linear scale. Oh, that's the input, so it's a perfect sinusoid. Let's look at the FFT now of the output. To use a Blackman window. Some other tutorials explain these windows better. So we see harmonic distortion here. Okay. Now, if you calculate the slew rate limiting frequency as the slew rate SR, that you have it in the datasheet, divided by 2 pi V output, you're going to see a frequency that is lower than this, and it is because it is you may not even visually see it in the time domain, but it's when you start to see harmonic distortion. Okay, so that's slew rate. Your job as a designer is to choose an operational amplifier where it's going to behave as ideal for the frequencies that you have. So you should not be able to see this slew rate. So if you have, for instance, in the case, an application where you're going to need to operate at 10 kilohertz with an output voltage of 12 volts, don't choose the 741. Okay, there are other operational amplifiers where it's going to behave ideal. Now, you may ask yourself, why are there so many operational amplifiers? Hundreds of op-amps. Why not just one or two that solves all the problems? It is because of these non-idealities. If you want to say, so you need to choose them for the particular application or the particular stage and the particular application based on what matters to you for that application. For instance, if you want very low bias currents, you may have operational amplifiers that have a MOSFET at the input and they achieve very low bias currents compared with BJTs. But you are doing that at the sacrifice of the offset voltage, for instance. And so, same thing. You may want very high bandwidth, very high slew rate, very low offset voltage, etc. Your job as a designer is just to choose the operational amplifier, and if one characteristic is optimized, the others, or some of the others, may be not as good. Okay, so that is slew rate limiting frequency. Now, if the voltage goes down, everything is fine. Okay. Now, let's put there a low voltage. I'm going to say like 0.5 volts. And let me increase the frequency. 100K. Okay, and let me actually do that. Now in this case, we have low output, and we have a high frequency, and we are seeing there. Actually, let me just do this first. 500K. Now we have two effects going on. We have the slew rate limiting frequency, but you also see a further attenuation, and in this case this is due to the bandwidth. Let me actually do this very low so that we eliminate the slew rate. You see, no slew rate, and we see an attenuation there, but the input and the output are sinusoids. That's due to the limited bandwidth. Let me increase this. Same thing. In this case, now we have an attenuation. Input sinusoid, output sinusoid, phase shifted. We expected a sinusoid of the same, being a follower, amplitude as the input. We see an attenuation there. And this is not a slew rate. In this case, it's this limited bandwidth, which we do a frequency response analysis by doing an AC analysis with a SPICE directive. That AC, like 10,000 decibels, 10,000 points, start at 1 Hertz, go all the way to 10 megahertz. I'm going to do this. If you have another SPICE directive for analysis, you need to comment it out. So I'm going to do a frequency response. So let's change the... Okay. Remove the phase. So what do we see? 741, no gain, so this will be the equivalent, the 3 dB should be the same as the unity gain frequency, and it's around a megahertz, okay? And so what we see here is that even at low gains, there is a maximum frequency at which you can operate, and then the operational amplifier is going to have an attenuation in that gain, which is linear. A sinusoid of the input, you get a sinusoid of the output, or the same frequency at the sinusoid of the input, but an attenuation of the amplitude, and you get a phase shift. So this is the difference between AC, limited bandwidth, or unity gain frequency. Remember, it's a linear limitation. Is independent of the output voltage. Even a small signal, you are going to see it, and it does not cause nonlinear distortion, only linear attenuations and phase shifts, versus a slew rate, the maximum rate of change of the output, and the slew rate is going to be dependent of the output voltage, the slew rate limiting frequency, also known as the full power bandwidth, and it's going to manifest itself with nonlinear distortion, sinusoid at the input, you get triangle at the output with that maximum slope that the operational amplifier has. Now, we're going to show also in this case that as you increase the gain, you are going to reduce the bandwidth, and that was the gain bandwidth product concept. So let me convert this non-inverting amplifier into, this following into a non-inverting amplifier with gain by adding some resistors in the feedback. So right now we have a gain of 1, right? And if I want to be able to program that gain to be higher than that, we can put a network, feedback network, right? Let's imagine I want a gain of 10. Well, I can put 9K here, 1K. Why is it that instead of doing, why do I use 9K as opposed to, say, 90 mega ohms or 900 mega ohms? And remember, the higher those resistors that they have, the more you're going to amplify the input offset current, the input bias current effects, etc. Okay. So let's go ahead, and in this case we should see a gain of 10. Let's do the transient first. I'll explain that phenomenon later if we have time. And let me go to lower frequencies. So let's start here with 1K input, input 1 volt, output 10 volts. Again, if you have an application where this is the frequency range where you're operating, and these are the output levels, it's ideal. Now, what we are going to see is that if we increase that frequency, we may lose some of that gain, right? So at 10 or 100K, we were expecting a gain of 10 and we are not getting it, right? Right? Even here we are already seeing an attenuation. We expected a gain of 10 and we are at 8, at 10K. Let's go ahead and do the AC analysis. And see. Remember before when we had a gain of 1? That we had all the way to 1 to a megahertz? Right now, we increase the gain by a factor of 10, we have a gain of 10 or 20 dBs, and we reduce the bandwidth. Now we are here. Okay, if you increase it further, instead of 9K you put 90K, it's going to even be reduced further. Okay, let me just show you by defining a parameter RF and doing a parameter sweep. So Spice directive, we're going to do step param RF. I'm going to do from 1K. Just a second. 1K gain of 2 to 90K increments of 9. So we have 11 simulations. And what we are going to see is that as we increase the gain, our bandwidth decreases. So at low gains, we are reaching here close to 1 megahertz. To increase the gain a little bit over 20 dBs, 100K, and this has to do with the gain bandwidth product, right? So to recap, there are two types of AC limitations or dynamic limitations. There is a small signal linear limitation. It is this one. The gain is not constant with infinite bandwidth. It has a roll-off. And that roll-off depends on this unity gain frequency that you have, that you can see in the datasheet. The frequency at which the gain of the operation amplifier is unity. As you increase the gain, you are decreasing that frequency. It is a limitation that is independent of the output voltage. You're going to see those attenuations even for small input very small input voltages or output voltages. It is linear, sinusoid at the input, you get sinusoid at the output of the same frequency, but you lost gain. It does not cause, therefore, nonlinear distortion. The other AC limitation is the slew rate limitation, maximum rate of change of the output with respect to the input, which for a sinusoidal input or any other input signals can be decomposed into some sinusoids, is going to cause nonlinear distortion because there is a maximum rate of change of the output, and that nonlinear distortion always is going to look triangular because it's that ramp. Okay? Thank you.